Hi guys, here's Cole to introduce the wearable metal detector vest.
Hello, here we are. We have our different components to our metal detection vest. We have our power source here, which is a rechargeable lithium ion battery. We have our control board here, which houses our detection circuit, and we have our electromagnetic coils attached to our medical back brace. And you can see the larger transmission coil here along the outside, and it has these two equal receiving coils on the inside. Hello, this is Austin Lindsay. In this section I will be talking about the clothing and other aspects of the metal detection vest in regards to its usability. The original metal detection vest we were given at the start of the semester was very bulky and difficult to transport, making it counterintuitive to its intended purpose of stealth. Our latest prototype, shown here, has all three coils mounted to a single fiberglass frame attached to a medical back brace. This design was chosen due to its rigidity, restricting movement of the receiving coils. Independent coil movement during sampling cycles would result in false detections. To better streamline integration of the control board and its connections to the vest, a casing with 16 I/O terminals was chosen to house the board. Connecting wires were soldered between major pins and ports on the control board and the 16 terminals provided by the housing. The original vest received power from a standard wall outlet via a 120 to 12 volt rectifier circuit. However, because cables are not very inconspicuous, we opted for a battery supply instead. We chose a rechargeable lithium-ion battery with a 6,000 mAh capacity and a 6-hour charge time. Other considerations include using non-metallic materials in the vest construction to preserve signal integrity.
Hi, my name is Napoleon and I had the coil section of the metal detecting vest. The coils for the metal detecting vest were designed to be sewn onto a concealed or stealth vest. We had 3 separate loops, 2 receiver coils on each side, and 1 transmitter coil on the back. This was the most appropriate approach for the best sensitivity. The receiver coils had an inductance of 171.4 microhenries, and the transmitter coil had an inductance of 224.1 microhenries. Using 2 receiver coils allowed for the differential amp to be used in the detection circuit. When no metal was placed in the magnetic field of the coil, the receiver coil would yield the same current output. Once a metal object was placed on either side of the vest, the magnetic field would generate a current through the detected object. The difference in the current output received would cause the differential amp to swing high or low relative to the object size. Some of the improvements we made to the coils were we wove the coils into a fiberglass back brace and reinforced it with a hot glue gun for a more practical structure and a low profile.
Hi, I'm Riley Klages, and the third area of our presentation today is the PCB and the programming behind it that makes it work. The 3 subsections of this topic concern how the circuit board couples with the external hardware, how the controller interacts with the circuit, and the detection algorithm. The 5 external connections to the circuit board are crucial for the operation of the metal detector vest. These connections include power, a single transmission coil, 2 receiving coils, and pins 9 and 12 for external alarms. These external alarms can include speakers, buzzers, bells, vibrating pieces, etc. For the transmit side, here we can see the PWM signal coming from the PCB in red, driving a series of BJTs and MOSFETs, driving the current through the transmission coil. On the reception side of the operation, the difference between the signals from the 2 receiving coils is taken. This DC output is then filtered and buffered for the next stage. This stage allows the chip to compensate for noisy metallic environments. For examples of the detection algorithm, sections from the transmit and receiving sections were taken. On the left, we see that the transmit pulse PWM timer section of the code writes how long the impulse of current is through the transmission coil, as well as the status of the sampling window. In the section from the receiving side, it is shown how the program compares the state of the signals from the receiving coils to the previous average value. The program activates an alarm on pin 22, one of the external alarm pins, if the average value returned from a sample window differs from the center value.